Okay, so we're recording. So let me just go ahead and try to cover a lot of the stuff that we kind of go through in this chapter just very briefly, and we'll try to get more examples in to these lectures now. So the first section of the chapter 25 is all about current. We use the symbol I for current. We define current as an amount of charge which flows through a given cross-section of a material in an amount of time delta t. So by convention, we assume that positive charges are moving, but we know enough electricity, we know enough about electricity at this point in the class that positive charge flowing to the right is the same as negative charge flowing to the left, right? And it just makes our analysis easier. We don't have to deal with minus signs because we're working with negative charge. So we choose to work with positive charges flowing in the opposite direction that the negative charges are flowing. And as long as we treat the magnitudes of the charge the same, then we get the correct physics. Okay, so what do we do with this expression here? Well, the first thing that we kind of do is we label this as an average current because we have deltas in there. And if we want to know the full instantaneous current as a function of time, we would take a derivative with respect to time. And that would be in the limit as delta t goes to 0, as one would expect. Now, it's only going to be a function of time if the flow of charge is changing with time, right? So if we just have a fixed amount of charge passing through a wire in a given period of time, then our current, is going to be constant because the amount of charge flowing doesn't change with time, right? So just a quick example here. So suppose we had some number of charges here flowing like so. Okay, let's suppose that we have roughly 10 to the minus 3. Let's put a number out in front. So 1.5 times 10 to the minus 3 coulombs worth of charge passing through cross section of a wire in a delta t of roughly, let's say 45 milliseconds. How much current do we have flowing in the wire? Okay, go ahead and calculate that real quick. Very simple example here, just get us warmed up so we're ready to do examples. What answer do you guys get for that? Just put your answers in the chat as you get them. And you guys can compare against each other. Seems like you guys are getting the same answers here, so that's good. All right, so let's go ahead now and move forward to this idea of current density. which I kind of explained answering that question before we got started here, but we'll just go through it again. Current density is this idea that we can have charges flowing in a wire, but that wire has a cross section with an area A. Now, in general, you don't have to have charges flowing in a wire with a fixed cross-sectional area. Okay, but for the purposes of our class, we're mostly interested in what's going on in wires and things, right? We want to be able to do circuit problems, and in circuit problems, the cross-section of a wire is the same, right? So we want to kind of take a look at this kind of simpler case. But the idea here is that there's an amount of charge flowing in the wire, and there's a cross-section for that wire, and we can calculate a current density by taking that amount of current and dividing it by the cross-sectional area. Now, if we want to be more precise, again, we would upgrade those deltas from delta to derivative with respect to the area here. And if we wanted to find the current from the current density, which sometimes we have to do something like this, we would integrate the current density with respect to the cross-sectional area, okay? Now, if we wanted to get really precise here, we could upgrade these guys to vectors, okay? But in this class, I don't think we're ever going to get to that stage where we need to do something like that. Again, we want to do problems involving circuits. Circuits are already interesting enough for us, you know, especially in terms of like engineering applications and things. And so we don't want to complicate the physics too much here, or the mathematics even. We want to just do our kind of usual approach of kind of keeping it simple and seeing what we can do from there. So this is what we'll use at a maximum here to get the current. Now, there is one more thing that we should probably acknowledge here, and that is that in this case here, we could have a current which depends on time. And of course, the current density could depend on time as well, right? And so we could also look at a relationship there where we have time dependence. Okay, so let's examine again this previous problem here. Let's suppose now the same example as before, the cross-sectional, not the area, but the radius there of that wire for the cross-section of the wire there is, let's suppose, is about 1.33 millimeters. Okay, so now what is the current density there? So go ahead and calculate the current density for that wire. Use the numbers you already have there in your notes, and I'll just kind of scroll down here and I'll get the next set of material ready while you guys work on that. Of course, you will see integrals sometimes, but in the case of the current density, not so often.
A quick question. Is the current one we calculated in the last problem?
Yes.
Okay.
Professor,
Yeah.
what is current again? I didn't write it down.
Current is the amount of charge divided by the time it takes for that charge to flow.
Oh, I meant the given current from the last problem.
I didn't give a current. You had to calculate that.
Oh, okay. Oh yeah, okay. Thank you.
Did you get it? Like point?
Yeah, I think it was 0.03.
Yeah. When you guys get your answers there for the current density, just put your answers in the chat and compare with your peers. Actually, now that I think about it, there's one more thing that I want to say about current density before we move on to the next part. I only see a couple answers given in chat so far, so I think maybe you need some more time.
Professor.
Yeah.
So I use the equation I over pi r squared, and I'm getting 5.4 times 10 raised to the power of 9. Oh wait. Yeah, I'm kind of getting what Jaime's getting.
Double check that you have your parentheses because you're dividing by, you're dividing by pi r squared. You need to make sure that you divide by that whole quantity.
So just to double check, so I do have 0.03 on top, and on the bottom I have pi, and then in parentheses I have 1.33 times 10 raised to the power of -3, and I'm squaring it because that's the equation for.
That sounds correct. Yeah.
Okay, so now I'll just put what I got because it is different, but.
It looks like most people are getting close to 6 kiloamps per meter squared. Why don't you guys go ahead and write down what you punched into your calculator so that we can help out these couple students who got 5.4 instead of like something closer to 6, like 5.9. So if you guys could do that, punch in what you typed into your calculator. I'm going to go ahead and write down the next bit here. So okay, so so John says probably use 0.03 instead of 0.033. Yep, probably. That seems like that could be it. Yeah, so it looks like you've done it correctly, or Phil just round it off to 2 sig figs. I would say that be careful about that. Remember, whenever you make calculations, always use exact answers until the very end. So you have to remember that you rounded your first answer, And then when you use that answer to calculate the second part, you have to go back and use the exact answer before you rounded, okay? All right, so let's go ahead and take a look now at what happens in a simple case for a wire to the current density, okay? Current density in a wire, we can look at as a nice expression here. And I'll go ahead and create a little bit more room here for us. Take a look at that. I'll bring this down further. We can look at current density as almost like counting the number of charges and multiplying by the number of charge, by the actual charge of each of those charges. So number of charges. So N is literally a number of charges. And then Q is the charge of each of those charges. So the charge of those. Actually, let's be more precise in our language here. So let's say number of particles, and then Q will be the charge of those particles. Just to make sure that we've got it like a precise definition here. So number of particles, and then the charge of the particles is Q. And then this term here is called the drift velocity. This is the velocity that those charges move with on average along the length of the wire. And so this velocity tends to be a small velocity. The average, the motion of these charges in a wire. Remember, we're dealing with electrons here, right? It's really electrons that are the charges that are moving. And so there's a lot of problems here with this equation, actually. This is a very introductory physics course type of equation with a lot of hand waving going on here. So the first problem with this equation is the number of particles, okay? We can't precisely count the number of electrons that are moving inside of a wire. That's impossible. Quantum mechanics denies us from being able to do this. Number two thing that's wrong with this expression is that it's not an exact equation, but it's an equation of an average. And so this really is the average current density averaged over a large number of electrons in the wire. Just to, can think of that as like a numerical average if you want. And then finally, third problem with this equation is the idea that we can assign a velocity to these particles. Again, this is something that's prohibited by quantum mechanics. Now, in the context of, treating this problem as kind of a classical statistical problem where these charged particles are placed in an electric field. So we have a wire here, like so, and we put an electric field in this wire in this direction. Certainly classically, we would expect charged particles to experience a force if they're positively charged in the same direction as the electric field, if they're negatively charged in the opposite direction. But quantum mechanically, we would expect no such thing to occur. Now, just kind of heuristically here, this drift velocity, what is this thing? Well, a lot of the charged particles inside of this wire here, and I'll just use a positive particle just because that's what we're assuming is moving in these types of problems, is kind of undergoing some sort of like random motion or pseudo-random motion inside of this wire. And that random motion is due to collisions with all of the neighboring charged particles in its vicinity. So other positively charged or negatively charged particles are kind of interacting with each other in this wire, kind of moving around and bumping into each other, so to speak. And that motion is pseudo-random. It's not entirely random, but it's modeled as it's modeled fairly well as like a random scattering type of problem. And if we were to apply this electric field, what happens to this scattering is that there's a slight bias now in the scattering. And so when this charged particle kind of bounces around all throughout the wire, eventually after a certain amount of time, it kind of ends up slightly moved, slightly displaced from its initial position. And so that's kind of the viewpoint that we'll take here when we look at this kind of expression here with the current density just kind of given in a very simplistic form, where you just count the number of charges and you say you multiply by the charge of each of those particles to get the total charge, and then multiply by this thing that we call the drift velocity, which is the velocity that these things would have if they were like Newtonian objects, you know, like a block of mass, and you applied a force on it. It would accelerate in that direction, but because it keeps colliding with everything in its area, then there's some sort of friction force involved there. And so that velocity, that terminal velocity that it reaches, ends up being constant. We call that the drift velocity. Okay, so hopefully that gives you a good picture of kind of what's going on there. This is a classical treatment of a very quantum mechanical problem. So it is kind of difficult to get a complete picture here. But that's the general idea, though. You have to think in terms of statistics almost for this. You think that it's kind of bouncing around randomly, but if we put it in an electric field, it will continue to bounce around randomly, but it will have a slight bias in the direction of the electric field if it's positively charged. And so if you average out all of that random motion, you get this average motion of it slowly kind of moving in one direction. And of course, remember, we're applying an electric field. Positive charges experience a force, and force is proportional to acceleration. But because this thing is bumping into all of its neighbors constantly, that represents a source of friction. And so that acceleration eventually becomes zero, and you reach a terminal velocity. And that terminal velocity is called the drift velocity. There's one more thing to say about that before we go to the next section. And that is that the drift velocity is very small compared to the random motion of the particles. So V d is very small.
Professor, why is VD very small if electrons move very quickly?
Because the rate that the electrons are moving, or excuse me, the speed that the electrons are moving around the atoms is far bigger than the drift velocity because of the frictional component. That charge, in order for that charge to move, it has, so let's say from one atom to the next atom, if you have a copper wire, right, electrons are free to move from atom to atom. That copper atom's electron has to bump into other electrons as it moves from one atom to the next. And so that interaction represents a large source of friction. So VD is very small compared to the random motion of the charges within their respective atoms. Oops. just to give you a sense of the kind of the speeds that we're dealing with here. So the orbital speed of an electron in a hydrogen atom, calculated classically using Coulomb's law, is roughly 10 to the 6 meters per second. And the drift velocity for atoms, say in a copper wire, depending on the potential difference across the wire, could range anywhere from, say, 10 to the minus 3 up to maybe 10 to the minus 2, something like that. So in that range there. Not very big. I probably we could account for a few more special cases if we say maybe 10 to the minus 4 up to, let's say, 10 to the minus 1. But you can see that it's far less than the orbital velocities of these charged particles calculated classically from something like Coulomb's law. Okay. Give you guys a second to kind of copy that down. And let's go ahead and do an example actually here for this before we get to resistivity. Just kind of carry on with that idea of keeping the examples coming. We'll change colors here. Oops. I like the examples. It gives a feel of the equations. Yeah. Calculate J and what was the other thing I was going to say? Oh yeah, the drift velocity. I'm getting this example straight from the textbook, by the way. So the other examples I gave were not from the textbook, but this one I'm just going to take it from the textbook because it's hard to come up with an example of this off the top of your head. Remember that there are lots of examples in every chapter in the book, and they should be pretty useful. I've looked at them for several of the previous chapters, and they're all good examples. This is a copper wire. That would be the diameter of the wire is 1.08 millimeters. Oh, sorry, 1.02. If you're wondering what I'm writing at the moment here, the free electron density, well, this is the number of electrons that are allowed to conduct electricity. So these are electrons that are in the conduction band of the metal. And so these are the ones that are allowed to freely move. When you apply like a potential difference to the wire. Notice the units here on the free electron density. So it's a density, meaning you need to multiply this thing by the volume in order to get the total number of free electrons. As a matter of fact, in this case, you're not given a length for the wire. And so what you'll do is you'll multiply by the cross-sectional area. Yeah, copied everything. Okay. So let me know if there are any questions here about the setup. I'll go ahead and get a picture down for you guys as well. So let's go ahead and maybe draw like a simple picture. Again, a lot of the pictures we'll have are just kind of like wires like this. So like so, and we have the radius here of the wire given in terms of actually the diameter, 1.02 millimeters. We have the free electron density in the wire is this number. So how do we get total number of charge here? So, oops. So current is Q over T. So free electron density times the volume of the wire would give you the total number of electrons. (2.1 times 10 to the negative 6 J). I'm not sure what you mean by that. You mean that you calculated the current density? You should put
you say
units.
it's because you asked calculate J. So
Yeah,
I
you
said
should put units.
Oh, okay, sorry.
Right, make sure you got your units right. And again, just type your answers into the chat as you get them. Oh, and actually, you know what? I kind of actually this is misleading what I said here. I'm thinking about this again. Now that I'm thinking about it, actually, the meaning of n here is not the number of particles. Everybody change this in your notes really quick. This is not the number of particles. This is the concentration of particles. Concentration. In other words, it is the density. So density of free charges. Sorry about that confusion there. Density of free charges. It has to be density, otherwise this thing will never have units of current over meters squared. Yeah, particles per volume, exactly. So J equals I over A. I'm not sure. I think you're combining two formulas there, or Phil. I think what you mean to say is J equals I over A equals NQ drift velocity. So
But can't you move the NQ and the drift velocity to the other side with I, or yeah, with I over A? Because doesn't J equal NQ and then the drift velocity?
well, certainly you can set the two equations equal to each other, but what are you trying to accomplish by dividing one formula by the other formula? If the two are equal, you divide one by the other, then you get one, right? You're not going to get anything else. Do you kind of get what I'm saying? Or
Yeah, because yeah, I get what you're saying.
so like, because I think what you're thinking of here is like take I over A equals NQVD. And see, if I just divide both sides by NQVD, then I just have one on this side. And NQVD over here on the denominator. So that doesn't really help me out to calculate anything. But perhaps you're after the drift velocity, right? So maybe don't divide by the drift velocity. And then you can see maybe you're on the right track.
Oh, okay.
A lot of you are coming in with some answers now that are pretty good. Just give another minute or two, maybe is enough to make sure everybody kind of has a chance to get it. I'm going to go ahead and scroll down past the problem at this point and write down some stuff just to be a little bit more time efficient since we kind of started a little bit later. And I'll just go over this as you guys kind of finish off that problem. So type your answers in, check your answers against what everyone else got there. If you don't want to type your full answer in, but you're seeing you're getting the same as everything else, just, punch in the chat, like got it or something like that to let me know that you kind of, because there's 18 people here and I only see maybe 3 or 4 answers. So just type, got it. Got the answer. It's been a couple minutes, so I don't see anybody letting me know they got the answer. Only Duke, Jonathan, Sean, and Orphil. Looks like I think you got the first part there. Do we need some more time on this one? Can you guys let me know? Do we need some more time? Just type in the chat if you need more time. I can't really see your guys' like thumbs up and that kind of stuff because I don't have two monitors here. I'm just on my new laptop. Still need to set up my my computer and stuff. Type in the chat if you need more time. Okay, so we'll keep going then. We'll go ahead and just keep going, since nobody's really saying they need any more time, so I'm going to assume we're ready to go. Let's talk about resistivity now. So when we write down Ohm's law for the first time, we tend to write it down in terms of conductivity, and then we never really talk about conductivity anymore, which is kind of strange. But essentially, the relationship between conductivity and resistivity is that they're simply inverses of each other. So we can replace conductivity here, sigma, with resistivity, given by this expression here. So we've done that in red on the right side there. And we can rearrange this equation here to get that the resistivity is equal to the electric field divided by the current density. And notice I'm not writing any vector signs in this equation. So we're working with magnitudes here. We're working with magnitudes and we're working in conductors. So magnitudes, because we're assuming we're looking at conducting wires. As a matter of fact, I don't even need to write the word conducting because writing down this equation assumes we're already looking at a conductor. So assuming wires of fixed cross section, meaning, you know, if we write down a radius of the wire, that radius never changes. Like even if we kind of like bend the wire a little bit or something, it just stays the same. So fixed cross section. And this idea of resistivity, as we're going to look at it, we're going to look at conductors here specifically. You can think of non-conductors, in particular semiconductors and insulating materials. You can try to think of them in terms of Ohm's law. For example, like you could think of an insulator as a conductor with infinite resistivity or a very, very large resistivity. And that can kind of be a model for an insulator. You can look at semiconductors, which what is a semiconductor, right? You can look at a model of semiconductors where they're good insulators until you reach a certain threshold. And you can think of that threshold in terms of the electric field if you want, or you could think of it in terms of like an applied voltage. The two would be related. So you can think of a semiconductor as kind of having a really large resistivity until you get to a certain amount of electric field. And then once you reach that electric field, then the resistivity goes down a significant amount, and then charge can kind of begin to conduct. So we can take a look at, we can go ahead and take a look at some pictures of that. Go ahead, ask your question.
I was gonna ask, I don't know if my mic is working that much.
It's working.
Okay,
Ask
so I
your
was gonna
question.
ask, isn't any material? I thought any material can give current, even rubber, if you reach a very, very, very high voltage.
Yeah, so there are, remember the chapter on capacitors that we just talked about when we looked at dielectrics specifically, right? We can think of insulating materials as being dielectrics. And so when we apply a really large electric field, we can eventually cause dielectric breakdown. And dielectric breakdown means you've applied such a large electric field that you're stripping charge off of the atom. So the electrons, you're just ripping the electrons off the atom because the electric field is so large. As soon as you do that, that means that that insulator is now conducting. The problem with insulators is that you have to apply a very large electric field to get them to start conducting. Whereas what classifies a semiconductor is that you can apply much lower electric fields to cause conduction. Does that make sense?
Yeah, so semi is just like a small amount of voltage. It's pretty high, but just kind of small compared to the insulators.
Right. So we'll try and take a look at that. I have some values from a table here that I'm kind of going to write down for you guys, just to give you guys some ideas. And we'll just look at the interesting ones. So here are some values for resistivity. And this is straight from a table in your guys' textbook. So I'll just list two conductors here, copper and gold. And then I'll take a look at an insulator, and I'll take a look at a semiconductor. So values for the resistivity for conductors, we have copper, which is what we use in a lot of electronics, right? Your house wiring and everything is in copper. Copper has a resistivity of 1.72 times 10 to the minus 8. Small is good here if you want charge to flow. And that has units of ohms, ohms times meter. Ohms times meter. I had to remember it there for myself there for a second. Okay, so small is good. So this is small here. This is small. Times 10 to the minus 8 is small. That's good. Small equals good for conductor. Well, okay, how good is 10 to the minus 8 though, right? You have to compare it to other conductors. Well, when you compare it to gold, maybe copper is not that good. For gold, we have, no, gold is higher, excuse me. 2.44 times 10 to the minus 8 for gold. And then silver silver, now this is where it kind of gets interesting. Silver is better than copper. So it's 1.47, roughly 1.5 times 10 to the 8. So you can, minus 8. So you can see silver is a better conductor than copper. Copper is a better conductor than gold, right? So the smaller, the better, because the smaller the resistivity, the smaller the resistance is going to be if you make a wire out of it. So that's what we'll look at for conductors. Okay. Now let's look at some insulators. We'll just look at like one insulator, and then we'll look at one semiconductor. Okay, so for insulators, they give glass, and there are many different kinds of glass. So this is going to be a range here. They say it's somewhere between 10 to the 10 and 10 to the 14. Again, if you have a specific kind of glass, you could write down a number, but there are many different kinds of glass. So in general, glass is going to range from 10 to the positive 10 up to 10 to the positive 14. So this is big, right? Big equals good insulator. Okay. If you have big resistivity, you're a good insulator. I'll just read off a couple other ones. So like quartz, 75 times 10 to the 16. Amber. Amber is the stone, the gemstone that the Greeks used to discover, or that they first discovered static electricity with. Amber, 5 times 10 to the 14. Teflon. Teflon is, they give 10 to the 13 here, and they say it's bigger than that. Wood, 10 to the 8 to 10 to the 11, depending on the type of wood. Okay, how about pure carbon, aka graphite? So semiconductor. How about graphite? They list graphite as 10 to the minus 5, 3.5 times 10 to the minus 5. So graphite is just pure carbon, 3.5 times 10 to the minus 5. Again, the units here are ohm meters. Okay, a couple of chats. How would they find electricity with a high insulator? Wouldn't it dissipate? Remember, if you rub an insulator, you can charge that insulator, right? A PVC pipe is an insulator, right? But you rub it with some fur, which is also an insulator, and you can charge those two materials. So that's how the Greeks discovered static electricity, by rubbing amber with some sort of fur. Okay, so graphite, 3.5 times 10 to the minus 5. They give pure germanium 0.60 and pure silicon 2,300. Okay, so semiconductors range. There's a large range. They're kind of the ones that are in between conductor and insulator, right? So they can have a kind of a huge range of values there. And in some cases, the resistivity will change on those materials. Speaking of a change in the resistivity of a material, I will now talk very, very briefly on the connection between resistivity and temperature. Now, you guys will discuss thermodynamics and temperature and things like that in the 3rd semester of this sequence in the 223 class, the modern physics. Normally, I would be covering this kind of, like temperature thermodynamics at the beginning of the semester with you guys, but Fullerton College just kind of does it a little bit different, and they put that in the 3rd semester. So I'm not going to touch on this for very long. I just want to kind of briefly introduce it, and then that's it. So resistivity, rho, changes with temperature. And the way to understand why it changes with temperature is because of that random motion I discussed before. I mentioned that in a wire, you have these electrons, which are kind of scattering all over the place in this sort of random motion. And that if you apply an electric field, then those electrons will still scatter around kind of randomly, but there will be a slight bias in the opposite direction of the electric field because they're negatively charged, right? So those electrons will have a slight bias in their scattering. Well, what happens when you increase the temperature of a material? When you increase the temperature of a material, you get more of that random motion. And so by increasing the temperature, you've added more random motion, more collisions, more interaction between those charged particles, and therefore more of this friction type force. And so by adding more friction to the motion of the electrons, you should understand that that would also increase the resistivity of that material. Yes, you should skip it. I didn't put any problems on any of the assignments involving temperature. So resistivity changes with temperature. And there's a nice simple model as to how it changes with temperature, and I'll just briefly mention that. There's some resistivity value that you measure at a given temperature, and then it changes. It changes linearly with change in temperature. And so this here is like the coefficient that tells you how much coefficient that tells you how sensitive a material is to temperature change. Resistivity is with temperature. Okay, so it's a nice little linear model. You measure the resistivity, let's say at 20 degrees Celsius, and then you want to know how that resistivity changes over time. You use a linear model like this one, where the amount the resistivity changes depends on this coefficient alpha and the amount of temperature change. And remember, in physics, we always want to make sure that we use absolute temperature. Whenever we put a T in a formula somewhere, we use absolute temperature, which is measured in Kelvin. Well, whenever you have a delta T in Kelvin is the same as delta T in degrees Celsius. So you can plug your temperature difference in here in terms of Celsius or Kelvin, and that will work. Now, we're not going to be doing any problems involving this equation here. So that's pretty much as I want to say about it. Let me go ahead and zoom out and create some more space here. And I'll bring it right back. Okay, so I see a chat. It comes up in one homework problem. Does it actually come up in one homework problem? Okay. I can. Is it an easier problem, or is it like a more challenging problem, Sean? If it's an easy one, maybe I can leave it on there so that way you guys can get a little bit of exposure to that. I'm not sure if you guys will specifically touch on this topic next semester. It might be a good idea to just do maybe one problem on it just to be a little bit more familiar with it. Okay, it involves just using that equation. So maybe it's a fairly straightforward question. Maybe I should leave it on the homework and just let you guys kind of figure it out. And then that way you'll have a little bit of exposure before you see it next semester. if you even see it next semester. Excuse me. So any questions about that? So in the book, they give a nice little plot of how the resistivity changes. And so it looks something like this here. So you measure the resistivity at any point here at some temperature. We'll call it T0, kind of, I think the book calls it T0. And that gives you a resistivity value, which you call rho zero. Rho zero is not just some constant for a material. Rho zero is the resistivity of a material at a standard temperature. Standard temperature of like 0 degrees Celsius, I believe, is what they use for that. Let me know. Oh, no, sorry. Excuse me. 20 degrees Celsius. So they use the values quoted in the table. They give 20 degrees Celsius. In principle, this rho zero and T0, it doesn't matter where you measure it at, as long as you measure it at 20 or 30 or 40 degrees, as long as that's what you mean when you put the subscript 0 there, then that's fine. And so the resistivity is kind of depends in the following way. It's kind of this curvy function here, but as long as your temperature changes are not very large, as long as your temperature changes are not very large, then you can have kind of like a linear model like this. And the slope of this line here is alpha. The slope of this line is alpha. And so that's where that alpha comes from there. So you're just getting a tangent line at some point, and you can measure that constant alpha for a somewhat small range of temperatures. It turns out for conductors, this linear model works pretty good. So for conductors, the linear model works good. For a fairly large, so I think in some cases, ranges can be as high as like 200 degrees Celsius, something like that for some metals. Other metals are a little worse. They each have their own curve for the resistivity as a function of temperature. But for most metals, it's fairly large. For a fairly large range of temperatures, this linear model works pretty good. But again, the larger your temperature range, the more you open up yourself to error, deviation from the true value. Okay. So I'll let you guys ask me any questions about that before I move on from that. So that's the last time that I'll talk about this, and I won't ask you any questions about resistivity as a function of temperature on the quiz or the test. So does anybody have any questions? So I think there are no questions. Let me leave you with one last bit of information that you can read about in the book if you want to. And that is, notice that this curve slopes upward, that resistivity increases as a function of temperature for conductors. Okay, what happens for semiconductors is different. For semiconductors, this curve slopes downward. Let's just briefly try to understand why it slopes downward. as the temperature increases, there are more, well, let's say free charge increases. That's kind of in the same light. Temperature goes up, the number of free charges goes up, okay? And so if the number of free charges goes up, then there's more charge that's allowed to move in that material. And so the resistivity actually goes down. Now, the question becomes, I think it's an obvious question. Now the question becomes, well, hold on, there's got to be a limit to this, right? We can't just keep increasing the temperature over and like more and more and more, just continue to increase the temperature to infinity and a semiconductor just becomes better and better, right? That seems like an impossibility, and it is. So as you increase the temperature more and more, you create more and more free electrons. But as you increase that temperature, those electrons undergo more and more random collisions with one another. And so you're increasing the resistivity, you're increasing the number of free charges and decreasing the resistivity, but eventually there will be a turning point because your semiconductor will become a good conductor. And then once it's a good conductor, then it's got to obey some law like this one up here for conductors. So there is going to be a turning point at some point where this thing begins to act like a conductor and its resistivity will start to go up. Okay, so physics has to be self-consistent, right? It can't just slope downward to zero. It has to eventually turn around and become more resistive. Okay, so that's just some food for thought there. I'm going to go ahead and clear the screen and we'll move on to resistance. Okay, so nobody is objecting to that, so we'll go ahead and do that. So now I will write down Ohm's law again, but I will actually call it Ohm's law for the first time. There's a reason I wasn't calling it Ohm's law before, and that's because it's not in its common form yet. So we're going to go ahead and write down Ohm's law now in the following way. Okay, so instead of J equals sigma times E, I've written it as rho times J equals E. And now what I want to do is I kind of want to work in a specific case where we have a wire like so. And this wire has an electric field in it, like so. And of course, if it's a conducting wire, then it also has a J, a current density in this direction. If we apply an electric field, then of course we'll get current flowing in that direction if we assume the charge carriers are positive, which is the assumption that we'll always work under. So we'll have positive charges moving like so. All of these charge carriers are identical. I didn't mean to draw any of them smaller or bigger than the other. They should all be the same size. And now we can start to ask questions like, okay, well, this wire has dimensions, right? So suppose the wire has like a length and it has like a cross-sectional area, A, right? And so we can kind of start to imagine, okay, in order to get this electric field inside of this wire, we would have had to apply a potential difference, right? We would have had to apply connect this thing to a battery, so to speak, right? So we connect this to a battery. Otherwise, how would we even have this electric field here, right? Well, the battery is going to supply a potential difference of delta V, okay? And if the current density there is constant and the electric field is constant, Well, then we know that we can write delta V as E times L, right? E times L. And the current density here, the current density is connected to the current in the following way. If we want the total current in the wire, I, but then we take the current density and multiply it by A, right? The cross-sectional area. Current density is amps per meter squared, right? So we multiply by meter squared to get the full amount of current there. And we, of course, then we have to assume that this wire is, constant cross-sectional area, right? It has to be a perfect cylinder there, and so forth. Okay. So when we apply this potential difference to this conducting wire, the electric field is constant. So the current is going to be constant. The current density is going to be constant. There's going to be a fixed potential difference between the two ends of the wire. But as we move along the wire, the potential is changing as a function of the length of the wire. Okay, so that's the one thing that is actually a variable here, is the potential difference as we move along the wire. But it's given by this nice simple expression here because the electric field is constant. Okay, Sean, so it wasn't the homework. The resistivity temperature showed up on just the optional video problems, so ungraded. Okay, so I threw up the video on there. All right, so there are no questions on temperature dependence for the resistivity. Take a look at that if you want to kind of just get a better understanding of what's going on in this class. It's definitely interesting. Okay, so I have this expression on the left side with J and E. Let me try to replace J and E with these other quantities, delta V and I. So the first thing I'm going to do is I'm going to write the resistivity in red. Let's write the current density in purple, kind of as I already did. And we'll write the electric field in blue as we already had it there. Okay, and then let's just replace these guys with what they will be in terms of the other parameters. Okay, so J here, we're saying I is J times A, right? Okay, so let's multiply top and bottom by A. So multiply top and bottom by A. Multiply top and bottom by A. And actually, let me go one step further here. Let's write a purple A with the J. Okay. So we have this extra A on the bottom here. And then let's go ahead and replace now, or let's multiply top and bottom of the right side by L. As long as I multiply top and bottom, I can do it just to the left side, right? I don't have to do it to the right side. As long as I multiply top and bottom on the right side, I don't have to do anything to the left side. So E times L divided by L on the right side. Okay. And so now let's go ahead and make some replacements. So I still have the rho here. Now I'll replace J times A with I. And I will replace E times L with delta V. And I still have these two terms in black here that I have to account for. I have an L on the right side. Let me multiply the L over. So it's L here and divided by A here. Okay, and now we see that whenever we have a linear relationship between current density and electric field, then we also have a linear relationship between the current and the potential difference. Excuse me. But there's this extra factor over here, and we need to figure out what to do with this thing. So let's take a closer look at it here. It's rho, L, and A. Rho is constant for a material. Rho is constant for material. So for example, if I say this wire is made of copper, then okay, it's rho is the same everywhere, right? It's a copper wire. It's the same all throughout the copper wire. Okay, now this L here is the length of the wire. So if I'm dealing with just one wire in my problem, well, then L is just a fixed value for that wire, right? So I could have a single wire. I could change that wire out with another wire to change L, and that would maybe change what the value of this this factor is. But as long as I'm working with the same wire, L is also constant. And again, the last piece here is the cross-sectional area. Now we're automatically assuming that the cross section of a wire is the same everywhere along the wire, of course. But again, we could change A if we swapped one wire out for another wire, right? So, but in all cases there, we have to change the wire in order to change this factor. So rho, L, and A are all constant in this particular problem. Now we could change rho by changing from copper to gold. We could change L by going from a short wire to a long wire. We could change A by going from a thin wire to a thick wire. But for a given wire, all three of these are constant. That tells us we should rename this factor. And since this factor has something to do with the resistivity, we call it the resistance. Just another kind of synonym for the same thing. And this equation now is the finalized version of Ohm's law. How do we know when to use 1 over sigma and not rho? Well, you can use either or in any case. You can always use rho or you can always use sigma, but you always just, the relationship is always the same, right? Rho is 1 over sigma or sigma is 1 over rho. It doesn't matter. They're basically the same measured thing, right? It's whether you measure 1 over it or you measure it directly, right? So, I mean, most of the time, I think our equation is going to involve rho. So if I had to say use 1 over the other, I would say use rho. So this equation now is the finalized version of not Gauss's law, Ohm's law. So this is Ohm's law, as we'll be using it throughout the class. So it says that the potential difference across a conducting wire is proportional to the current in the wire, and the constant of proportionality, remember this R parameter here, this R is the resistance. It's made of the resistivity, which is constant, the length of the thing, which is constant, and the cross-sectional area of the thing, which is constant. So R is a constant. So the potential difference across this conductor is proportional to the current that flows in the conductor, and the constant of proportionality is the resistance. Okay, so Ohm's law says delta V is proportional to current. Potential difference is proportional to current, and the constant of proportionality is the resistance. So we call this resistance. I didn't write that yet, so let me go ahead and write that. And now you might be wondering to yourself, okay, we did all this stuff assuming that we had a wire, right? Well, okay, we didn't necessarily need to call it a wire. It could have been some other thing that is cylindrically symmetric. And when we apply a voltage to it, it has a constant electric field. Okay, that's just a conductor. So really the only thing that went in here was that this thing has to be a conductor and it has to have fixed dimensions. And furthermore, if it has some other symmetry that's not cylindrical symmetry, we could repeat the same analysis and maybe something would change a little bit. I'll tell you exactly what would change. What would change here is J times A would no longer be valid for the current, but we'd have to do like a little integral, for example, if we had a sphere. But again, it wouldn't be that difficult. And ultimately what would happen is we would still write down this expression here. We would still write down this expression. And once we wrote it down, we would understand that R has a meaning independent of rho times L divided by A. Okay, so this equation works. This equation works for all geometries maybe I should not say all geometries. Let's say for all let's say this equation works for, let's put it this way. This equation works for any conductor but do not use R equals rho L over A unless the conductor is cylindrically symmetric.
Professor, how
Yes.
often does a question with a conductor that's cylindrical come up?
Well, any problem involving a wire, you'll assume that it's cylindrically symmetric. Most problems have some sort of cylindrical symmetry, but of course, you may come across a slightly more challenging problem where you don't have cylindrical symmetry. So I would say, like, anytime you hear the phrase wire, it's cylindrically symmetric. And in most cases, you'll have some sort of cylindrical symmetry.
Okay.
All right, so let's use Ohm's law now. Let's use Ohm's law. So just to get you guys, I'll just throw an easy one at you, okay? So before we had a wire with 1.67 amps of current flowing in the wire, and there was a little bit of information that wasn't given to you guys in the example. I didn't write it down, but it was talking about this current was flowing through some 200-watt light bulb, like super bright light bulb. Well, if that light bulb is plugged into the wall here in the United States, it would have 120 volts AC applied to it. Just assume it's a DC voltage. So what is R for that light bulb? So calculate R there. So another example. And while you guys do that, I will write down a follow-up example. So example 2. Oh, I see a couple of chats. Let me go ahead and, okay, just go ahead, put your answers in there, and then everybody just put your answers in the chat just to check with others. I'm going to go ahead and write down a second part here now. So suppose the filament is 3 millimeters. I should probably give a material for that. So suppose the carbon. Actually, did I misspell filament? Is it filament or is it fili? Let's look it up real quick. Yeah, it's with an A. So I spelled it wrong the first time. This is correct. I suppose the carbon filament is 3 millimeters long. Carbon has a resistivity. I think I wrote it down before actually. Oh, but it's I deleted it. So let me go find in the book real quick. I'll go find the carbon resistivity. Seeing a lot of chats. So ohms. Yeah, okay. Looks like you guys are getting it. For some reason, my table isn't loading. Let me try signing out of mastering and then signing back in so I can get the table. Unless somebody remembers the value that I wrote down for graphite, we can just use that value for carbon. Although a filament is not the same as graphite, that would still be a decent approximation. We'll just go ahead and use that value. That wouldn't be exact. An actual filament is a little bit different than just like straight carbon, but it's a composite material, mostly carbon. So, okay, so Sean gives us 3.5 times 10 to the minus 5 ohm meters. So we'll just pretend that that's the exact resistivity for the carbon filament. Let's say calculate the, well, let's do radius. Calculate the radius of the filament. Right. So we know the resistance from the first part. We know the length and we know the resistivity. So we should be able to calculate the cross section of the wire and therefore get the radius. And after this example, I'd like to take a break. So why don't you guys work on this example, get your answer, throw it into the chat, and we'll meet back in like 10 minutes. So that'll be like 5 minutes to finish off this example and then a 5-minute break, some combination. If you finish earlier, then you get a little bit of a longer break. So meet back at 4:04 p.m. and I'll see you guys then. Are we here? Is everybody here? Everyone back? Say something in the chat if you're back. See a lot of people punch their answer in too. That's good. Looks like we have a consensus there. Okay, so I think pretty much everybody. How do you guys like the like going through like with examples like this? I know they're super simple examples, but like is it good to kind of break the flow and just kind of work on something like that? I know Orphel already said he likes it. Okay, David likes it. Okay. Okay, so we like it then. Okay. Okay, so we'll try to keep doing it that way. Okay, so we're done with that example. So we'll go ahead and we'll move down now. Now, the next thing in my mind that I'm thinking is if we want to apply this to circuits, I don't know if this is the way the book does it, but this is the next logical step in my mind, is to say, okay, well, we had this situation where we have this conductor like so, and we connected it to a battery. Well, what if we took a second conductor and connected that to the battery as well? You guys see where I'm going with this now, right? We saw this kind of set up in the capacitors chapter. And so now we have two of these quote unquote wires. In reality, they're just some conductor. And furthermore, we would eventually just call these things resistors. So let's go ahead and do that now. So this is like resistor 1, and this is like resistor 2. And what kind of connection? So this is a question for you guys. What kind of connection am I showing here on Paint? Is that a parallel or a series, or it's neither, or is it both? Parallel, good. Okay, so the answer is parallel here. Orphil, I like your thinking there on that. That's a good way to think about it. That actually helps you remember. So if we were to think of this situation, let me ask you a follow-up question. So this is a question for Orphil. So he's thinking, let's double the area because now we have two of these guys. I like that idea. So if I were to double the area, what would happen to the resistance, the overall resistance of these two kind of combined resistors? Would it go up or would it go down?
If you doubled the area, I'm looking at the equation R equals length over sigma A. So because you double the area, it's gonna make the what do you call it, the resistor decrease by 1/2, right?
Right, exactly. So having resistors connected in parallel decreases the resistance. Let me ask a follow-up question. This is a question for anyone. Now, if I were to take these resistors and connect them in series, what would that look like? Well, it would look something like this. By the way, the idea of doubling the area there, you could only apply that concept if you had two of the same resistors, right? So they have to have the same cross-sectional area because you're saying it's twice as much now. So be careful about when you think about it that way, but that kind of is the general idea. If you connect resistors in parallel, then their resistance decreases. So here we have two resistors connected in series. Now what happens? So this is anybody can answer this. One over area plus one over area is not the right way to go about this. Does anybody have any input on this one? What's kind of an analogous way that we could think about this particular case here? If we had these two identical resistors, well, certainly their area, we couldn't imagine it being more area, right? But could we imagine, maybe I'll give you guys a hint, could we imagine this is now like a resistor of a longer length? Would that be a decent way of looking at it?
So, Professor, would you do 2L and then minus the space in between?
So imagine there is no space in between. So that this thing right here, these wires have zero resistance. They do not pose any resistance whatsoever to the motion of charge. So imagine this thing is just like two resistors smacked right on top of each other. So ignore that space in between. Exactly.
So then this would double the resistance, right?
It would double the resistance, exactly. So in this case here, R should go down. So this is parallel. This is parallel. R goes down. And then when we have series, R should go up. More resistance. Okay. But let's see why that's the case. Who remembers what must remain constant for any two circuit elements? You could think in terms of capacitors. Who remembers what must be constant for any two elements connected in parallel?
Voltage.
Voltage, right, voltage. So delta V is the same. How about for series? What's going to be the same when we have these two connected in series? Certainly, it's not going to be the voltage, right? It was not voltage for capacitors.
V per charge, all the same.
So, Duke, elaborate on that a little bit. You're saying the charge is the same, but since we don't have capacitors, we don't have a buildup of charge, right? So what about the charge would be the same?
I mean, the current, since in this case, talking like the amount of charge, so wouldn't it be current?
Right, exactly. So instead of charge building up, we have like a flow of charge. That's got to be the same, right? So the amount of charge that flows through these two resistors has to be the same. Now, that plays into what we talked about earlier, Kirchhoff's current law. So if I had a current through resistor 1 that was different than the current through resistor 2, then one of those resistors must be accumulating some charge, right? And then we can't have that. We can't have charge just building up on one of those resistors for no reason, right? There's no reason that a conductor would just start to accumulate charge in that fashion. Now, if it's a capacitor, that's a different story, right? Capacitor is designed in a way to store charge. But we're talking about just a conductor here for these resistors with no spatial gap between two plates. And so in this case, the current is the same through these two elements. When I say the word element, what I mean is an element of a circuit. So an element could be a capacitor, it could be a resistor, it could be an inductor, it could be some other circuit element that we haven't talked about before. So in general, even for capacitors, when capacitors are connected in series, the current flow is the same, but eventually the current stops flowing because the capacitors become fully charged. And then there's no more current flow once that happens. So even in the case of having two capacitors in series, the current is still the same. Okay, so knowing that the voltage is the same for resistors in series, I'm going to go ahead and cut to the chase here on this because we've seen this analysis before already. I'm going to replace now this idea of a resistor with this idea of a resistor. So just kind of a jagged line, and it has a resistance value R. And so I now want to look at a situation where I have two resistors in parallel, and they are connected to a voltage source. Matter of fact, we have N resistors. So this one has a resistance R sub N, this one R1, this one R2, dot, 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 up to Rn. All of them share the same voltage. So if I were to replace all N of these resistors with an Req, excuse me again, they would have, again, the identical voltage source here, but this Req is now representative of all N of these resistors. Okay.
Professor.
Yes.
I had a question on the previous thing we just did. Is it safe to say that if you have parallel cylinders, the area would multiply by the amount of cylinders you have, and then if you have
No. Nope.
no?
Let me stop you right there. No. The answer is no. You could add the areas, certainly, but provided you had that same symmetry, the same cylindrical symmetry for both of them, you could add their areas, and you would end up with, I believe, no, I think even that's incorrect. No, only in the case where they're identical does thinking about the areas work. So don't do that in general. That's a terrible idea to do that. That's why I'm doing this right now, is to show the general formula. Okay.
Okay. Yeah.
Okay, so Req, what is it in terms of these other R's, R1 through Rn? Well, again, we said we share the same voltage. So I can write down Ohm's law for each of these resistors, but the voltage is the same. Of course, if the voltage is the same and the resistance is different for each of those resistors, of course, the current through that resistor must be different as well, right? So I've subscripted I1 all the way through IN. However, the current that flows through the battery should be the same. The current that flows through the battery should be the same current. Which means that all of these currents here, I1, I2, dot, 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 IN, according to Kirchhoff's current law, should all add up to IN. And we can see that because this total current I comes into this point here, and I1 leaves and I2 leaves. But then I2 enters this node here. Oh, excuse me. That's not I2. Let's call it I prime. So I prime enters this node here. And of course, I2 comes off of I1. I've kind of drawn that poorly there. There's a little hook there that shouldn't be there. I prime comes in to this node, and I2 breaks off across the resistor R2. And then another, let's say I double prime goes again, and then I3 breaks off, and then an I triple prime, and then an I4 breaks off, and so forth. And if we apply Kirchhoff's junction rule, it's going to tell us that the sum of all of the currents from I equals 1 to n have to add up to the total current across the battery. And there's a nice simple way of thinking about this. The voltage source here supplies a certain amount of current to the circuit. And then that current is divvied up between each of the resistors based on how resistive they are. So higher resistance means less current, lower resistance means more current. And the current is divided up amongst all of these resistors. And there's only a certain amount of current that's available. And so all that current is split along each of those branches of the circuit with R1 through R sub n. Then once those currents pass across those resistors, they then have to recombine on the other side in order to conserve charge. Okay. All right, so what do we do now with this information? Well, I can take Ohm's law for the equivalent resistor. So Ohm's law for the equivalent resistor says delta V equals I times Req. And since all of my delta V's here are the same, what I can do is divide by Req to cancel it on this side so that I just have the current I, and then I can substitute this into this expression here. So that I have the sum over each of these currents from 1 to n. Is equal to delta V, let's color code it here, delta V over Req. But then, of course, I'll want to replace this guy as well. And I can replace this guy with delta V over R sub I from 1 to n. And of course, now we have exactly what we're after. We saw this already with the capacitors, except it was the opposite for capacitors. When capacitors were in parallel, their capacitances added. Now, when we have resistors in parallel, it's the reciprocals of the resistance which add. Giving us 1 over the equivalent resistance. So this is for resistors in parallel. So parallel only. Now, remember, there's an alternative formula for this. When we just have 2 connected in parallel, we can say product over sum. R1 times R2 over R1 plus R2. I'll let you kind of figure out where that comes from. We did go over it for capacitors, so go ahead and review your notes on that. You can go through the algebra to derive that formula. It's not that difficult. And again, that product over sum, again, is only for parallel. Okay. Let's take a look at a real simple example. Oh, go ahead, Orphel, you have a question?
Yeah, I was gonna ask. So the formula we have, the sum of n equals 1. How often are we gonna use this formula, or are we gonna use this formula, or are we gonna write it as a different, like in a different form? If that makes sense.
We just did write another form. You want to use the, I think I know what you're asking. You're asking me like, when is it better to use the top formula? When is it better to use the bottom formula?
Yeah.
Use the bottom formula if you have 2 or maybe 3 resistors in parallel. It's a little bit faster. If you have 4 or more in parallel, I think the top formula is much quicker.
Okay.
Let's take a look at a very special example here where we have 2 resistors, and I'll let you guys calculate this as an example here. So 12-volt battery. It doesn't matter what the voltage is here, but I'll just write this down just for completeness here for the circuit. We'll have an R1 and an R2. And I want you to assume that R1 is equal to R2, and that is equal to R. So this is part A. What is REQ? Sorry, REQ equals question mark. And then for part B, and I'll give you a part C as well, just have a couple cases here. For part B, assume that R1 equals 2 times R2. And for part C, assume that R1 is equal to, just go ahead and do it with 3 R2. Okay, so different ratios of the resistors. And it might be nice to see the answer that you get, and that might be useful when you come across a problem on the homework and you see, oh, this resistor is twice as big as this one, so I know the answer is going to be this. Okay, so go ahead and work on that real quick. I have something I need to do really fast. I'll be right back in like 2 minutes. Okay, I'm here again. Do we have answers for part A? Go ahead and punch it into the chat if you have an answer.
Professor, were we given the resistance?
No.
Because it's because I'm not quite following. If R1 equals R2 and that equals R, isn't that just like, I don't know, to me it looks like that looks like an answer. I don't know what you asked from us. So
Right here on the side, what is REQ?
oh, for each one, right?
Yes, for A, B,
Okay.
and C.
Okay.
So you don't need to have a numerical value for this problem. Do we have answers for part A yet? Or Phil, you can simplify your answer for part A. A couple people putting answers in. Looks like those of you put your answers in, or you've got it. Okay, so we'll go ahead and move on to series resistors. Since everybody is getting that one. So now we imagine the following scenario where we have two resistors or n resistors connected in series. Oh, whoops. And then dot, dot, dot out to the nth resistor. So again, it doesn't matter what the potential difference is here, but R1, R2, all the way out to Rn. Let's just draw it in for completeness there. All of these guys are in series, and we already said that I was the same, right? Or rather, I is the same. Okay. So it's not the voltage is the same anymore. The voltage is changing as we cross each of these resistors. There's a voltage drop, delta V1, delta V2, all the way out to delta V sub n. And so now it's Kirchhoff's voltage law that we have to apply here. Kirchhoff's voltage law will tell us that if we sum up all of the voltage drops across each of the resistors, delta V sub I, then that should be equal to the voltage being supplied to the circuit, delta V. Now, the other way to think of it is that we sum up all of the voltages and set it equal to 0, and then the voltage of our battery would be positive, and the voltage drop across all of these resistors would be negative. And so it would really be like delta V minus delta V1 minus delta V2 dot, 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 all the way out to minus delta Vn, and that would be equal to 0. So we could write that as well. Or delta V minus delta V1 minus delta V2 minus dot, 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 minus delta Vn equals 0. So that's another way of applying Kirchhoff's voltage law there. Same exact equation, just rearranged slightly. With that in mind, now we can write down Ohm's law again, except we have to be careful. So delta V1 is equal to I1 times R1. But I is the same this time. So let's ditch the subscript on I. And then, of course, delta V2 is I 2, but I is the same. So I2 equals I times R2, dot, 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 all the way down to delta Vn is equal to I times R sub n. And now remember what our goal is here. We're trying to replace n resistors with one equivalent resistor. So now we write down Ohm's law for the equivalent resistor. And that would be that delta V, which is the potential difference across the resistor, because it's the only element in the circuit here, is equal to I times Req. Remember, I remains the same because we started with series here. So the current in the top circuit has to be the same as the current in this equivalent circuit here, this little one in the bottom. So now what we want to do is we want to use the fact that I is the same everywhere and write down that delta V divided by let's go ahead and let's actually go ahead and use the summation that we wrote before. So let's go ahead and sum all of these terms up now. Okay, we'll go ahead and write down a sum now. On the left side, we would have that this is the sum of from I equals 1 to n of delta V sub I. And that would be equal to the sum of I times R sub I, and this sum would also be from n equals 1 up to n. Oh, sorry, I equals 1 up to n. I equals 1 up to n. But the current here can pull out of the summation. It equals I times the sum I equals 1 to n of R sub I. And on the left side, what can we do on the left side? Well, if we look up at our Kirchhoff's voltage law here, and I know I'm not using much color here, sorry about that. Here is what Kirchhoff's voltage law says. Whoops. Kirchhoff's voltage law says that the sum of all the delta VI's is equal to delta V. So let's go ahead and put that in there. So this is delta V now. And we can rewrite delta V again as I times Req. And now we see what's going on here. So, whoops. Let me get out the red here and we cancel I on both sides. And so we finally have now Req is equal to the sum from I equals 1 to n of R sub I. And this formula works for series. So resistors connected in series, if you want to replace them with an equivalent resistance, you sum up the resistances of those resistors in series. Okay. So now do that same example that I told you guys before, where we have two resistors connected in series, like so. So R1 and R2 connected to some, let's say 12-volt source. What is Req here for the following cases? Part A, R1 equals R2 equals R. Part B, R1 equals 2 times R2. And part C, R1 equals 3 times R2. So go ahead and work those out. And it is 4:40, so class is over. So if you want to, you can just go ahead and work on that example on your own time, right? Just write that down, copy that down, and work on that outside of class. That's fine. If you have any questions for me, ask questions now. I actually have to go. So if you have a question, like, please just ask it now. Okay, so I'm going to assume there are no questions. No one has spoken up. I'll just give you the answers here for this example, since nobody will check answers against each other. So for part A, it should be 2R. For part B, it should be 3R2. And for part C, it's going to be 4R2. That one is just a nice, simple, easy one. Okay. All right, so I'll see you guys on Thursday.